M. Karthik Kumar Reddy, working as an assistant professor in Nalla Narasimha Reddy Education Society's group of institutions. In the Department of Civil Engineering, in Foundation Engineering subject, in Unit 2 Slope Stability. Now let us look into the ordinary method of slices. In this method, the potential failure surface is assumed to be circular arch with center O and radius R. The soil mass that is ABCD above a trial surface AC is divided by vertical plane into a series of slices. As we have discussed with that, one of the limitations of the undrained slope stability analysis with phi is equal to 0 analysis is that determination of area and then determination of the weight and then D. So here what has been done is that the portion within the whatever the soil mass ABCD which is undergoing failure surface is divided into number of slices. The number of slices it depends upon by convenience it is actually divided, and the slices are divided such a way that they have some uniform horizontal distance, not necessarily uniform but mostly the uniform horizontal distance, and the base of each slice is assumed to be straight line, and so the circular arc is assumed to be a straight line, and factor of safety is defined as the ratio of the available shear strength to the shear strength tau m, which must be mobilized to maintain the condition of limiting equilibrium. So here what actually we can say is that the ordinary method of slices satisfies the moment equilibrium for circular surface but neglects the interslice normal forces. That is here the normal forces on the slices and tangential forces. So this is a typical slice. So the free body diagram of a slice in case of a ordinary method of slices where there is a vertical force which is shown that this is W is the weight of the particular slice. If there are n number of slices and if this is the ith number of slice, then the weight of slice is W into I, and this is the resisting force that is S, and this is the normal force that is denoted by N dash. So it satisfies moment equilibrium condition and neglects interslice normal and shear forces in this direction, one acting downward and one acting upwards, and it gives the most conservative factor of safety. So this gives the most conservative factor of safety, basically useful for demonstration. So ordinary method of slices the moment equilibrium for slip surface but neglects both interslice and normal shear forces. The advantage of this method, if you look into it, simply in solving the factor of safety, since the equation does not require any iteration process. So this is described in the form of a figure which is actually shown here, where this is a typical slope and this is ABC. This is the failure surface which is assumed to be one of the potential failure surface which is represented by dotted line. There can be innumerable number of failure surfaces, and but ABCD in this particular case is assumed as ABC is assumed as a failure surface, and D is the point of the crust, and O is the center of rotation, and R is the radius of rotation. And if you divide these slices of certain horizontal length, let us say it is B, and if you consider the free body diagram of this thing, and it actually has the normal forces E1 and E2, both are different, and x1 and x2 the shear forces. When you do not consider these forces, that is E1 minus E2 is equal to 0, and x1 minus x2, when coming to E1 is equal to 0 and E2 is equal to 0, x1 is equal to 0 and x2 is equal to 0. And this is why from the vertical this is the weight which is actually assumed to be weight of each slice. That is the center of this slice of width b. Horizontal distance and the arc is assumed to be a straight line. This is the tangential force, and n dash is acting on the base of the slice, and mu L is acting as a pore water pressure acting on the base of the slice. So this is n dash UL which actually gives this normal force, and this angle which is subtended from this n dash directly extends to the center of the rotation. That means you can see here in this figure this angle is called as the alpha. So as we travel from the from top side to bottom side, crest to toe level, the angle alpha changes that can be noted from the here. So the method of slice from the limit equilibrium conditions point of view, it can be given as factor of safety as tau f by tau m. The factor of safety is taken to be the same for each slice, implying that there must be mutual support between the slices, and the force must act between the slices, and the total weight of the slice W is equal to gamma WH. So if you consider this slice of width b, and the height is actually measured at the center of rotation, that is the height which is actually regarded as the height of the slice. This is the height of the slice at the center, in the where weight is actually acting, and then the weight is equal to gamma into b into h. And if so, let us assume that in the determination of this we are having a given slice, there are 3 layers of soils. Then we have to take gamma 1 into h1, gamma 2 into h2, gamma 3 into h3 into b. The b is nothing but the width of the slice. The length L is penetrated to the plane of that figure. What we consider in one matter, the total normal force N is equal to sigma into L. Sigma is the normal stress acting over the length L. We consider that 1 meter. So it is the force is nothing but sigma into L into 1. So this includes N dash is equal to sigma dash L, and U is equal to UL, where U is the pore water pressure at the center of the base, and L is the length of the base, and the shear force on the base is nothing but T. T is equal to tau m into L. The L is the length along the failure surface in a given slice of having width B, and the total normal force on slice E1 and E2, and the shear forces on the slides are X1 and X2. So the method of slices considering the amount about O is the sum of moment of shear forces T on the failure arc. Arc must be equal to the moment of the weight of the soil mass ABCD. So this we can write as sigma T into R is equal to sigma W R sin alpha. So by writing using T is equal to tau m into L is equal to tau m. Tau m is equal to tau f by factor of safety into L, and we can write sigma tau r as sigma tau f by factor of safety. L is equal to sigma W sin alpha. So factor of safety is given by rearranging these terms. We can write factor of safety is equal to tau f into L divided by sigma, that is nothing but the resisting portion divided by the driving, that is disturbing one, W sin alpha. So factor of safety is nothing but sigma tau f into L divided by W sin alpha. In this way, this is the form in the limit equilibrium. For an analysis in terms of effective stress, we can write factor of safety is equal to sigma C plus sigma dash tan phi into L. Also by writing sigma dash into L as N dash, we can write C dash into LA plus tan phi dash into sigma N dash by W sin alpha. So equation 1 is exact, but approximations are introduced in determining the forces N dash. So in factor of safety is equal to C dash into LA plus tan phi dash. In case if you are having a cohesionless soil slope, then we get factor of safety is nothing but when c dash is going to be 0, the first terms will get cancelled, and where we have tan phi dash into sigma dash and sigma dash n dash by w sin alpha. So this can be used for both undrained, the short term stability, as well as for the long term stability by substituting the relevant characteristic strength parameters.